All right, how's it going? Made it to Friday.
Hooray.
Hooray. So you probably already realized this, but there's no class Monday. Everybody knows that? Okay. So I won't be here. I think the building's actually going to be locked. All right, so questions?
Have you already started checking the programs that we
I have not.
We've been up all night grading.
I've been watching the clock, waiting for 8 a.m. so I could start.
We all put delays in our programs.
Excellent, excellent. It's actually pretty fun playing like 60 or 70 games of pickup sticks times 3 or 4 games each, so it's an altered state. Yeah.
So I tried using a debugger on the stick program yesterday, and there were a couple issues I ran into that I wasn't sure about, and that's every time it requested an input from fkS or tried to use like scanf, it would give me some weird error like file input output underscore fkS not found.
Yeah.
And then IO fkS dot C.
So let me show you how this works. Okay, that's okay. They have little slide things on top. They're really annoying. So this was our sort program from yesterday, and let's start debugging this. And I'm going to do next, and their size, and it's about to do a printf. And if I say next, it will execute that instruction, and it will come back to me when it gets to the next statement, which is 14. But if I say step, that will actually take me into the next line of executable code, which is the beginning of this function called printf. So if I say step, it's debugging printf right now, right? And it tells me that it called this thing underscore IO underscore puts. It had an argument which was str, which was equal to this, right? That's what it's being asked to print. And it's currently at line 33 of IO puts.c. That's not my code. Okay, that's runtime library code. And it's unhappy because it doesn't know where that source file is, so it can't show me the source code. And I can continue trying to step. And so now it's at line 35. Who knows what that does? And now it's inside stringlen avx2, and it's debugging this code that I didn't write, right? This printf code. So now it's doing string length, and that's something that apparently is assembly language. It's got a .s. So if this happens, sometimes you can get out of it. If you keep stepping through it, chances are you're going to encounter an error. Okay, and it'll end your debug session. But sometimes finish will get you out of there. So finish finishes the current call that it's in. So it was in this call to string length. It finished that, and now I'm back in IO puts. And if I say finish, now it comes back to my main program. So finish is your way to get out of that sometimes. And now when I'm about to call fgets, I'll say next instead of step, and it gets my fgets input. And then we can continue.
It also didn't want to start at my main program. It wanted to start at a function. It kept wanting to start at the print stick function.
Really?
Yeah, it was really strange. I had to put a break. I put break in main, and then it would go through. But otherwise, it would start at line 88 or something.
That's odd. So you were GDBing the name of your main program?
Yeah.
And if you run your main program, it works normally without
Yeah.
GDB? That's odd. So sometimes you can say break main and then say start, and then say continue if it's, but it should stop at that point at the beginning of main.
Yeah, putting a breakpoint at main helps.
Yeah.
I got GDB to do a lot of weird stuff for me.
Yeah.
I got like a thing where it would skip the draw stick loop, and then when I plugged it into GDB, it wouldn't skip it, it would infinite loop it.
Okay.
Oh, that's interesting.
What operating system? This is on the Linux server?
Yeah.
Okay. That's weird. It's possible that if something weird is going on with memory, like you've got an array out of bounds or something, that can cause weird behaviors, but this doesn't sound exactly like that.
I think it was that it was trying to start at the draw sticks function, and
Yeah.
it wasn't getting an integer passed to it, so it was starting with 0 and then checking if it was less than 0.
That's odd. Any chance you forgot a -G on one of the things you compiled?
Yeah.
Okay, so when you compile with GCC-G, you've got to have that -G on everything that you compile. If you have one function and you forget the -G, right, that'll trip up the debugging session. You can show me later if it's reproducible. Be interesting to see.
Did you say -G has to be included on every file?
Yeah, so if you compile in one line, right, so if you say gcc-o main.c, stick.c, that works fine, right? If you just throw a -G somewhere in here, all of these will get compiled with -G. But if you compile separately, and we haven't really talked about this yet, but we're going to talk about this soon. Right, if you compile these separately, you got to have a -G on each of those, and you got to have a -G over here. And if I forget it right here, then when I'm debugging and I try to go into stick.c, it won't have the source code and symbols and so on.
What would be the advantage of compiling separately?
Oh, the advantage is that main may be 1,000,000 lines of code and stick.c may be 10 lines, and I make a change to stick.c. If I do this, I only compile 10 lines. If I do this, I compile 1,000,010 lines.
That makes sense.
So think Linux, think thousands of functions, and you're making a change to one. So you just recompile that one, and these are .os. So when you compile a C program, if you say -C, it says, I'm not trying to build an executable. I just want to compile, right? So remember, there's compilation, and then there's linking, which gives you an executable. So if you do a -C, it gives you a .o version of the file. And then this says link those .os together. So we're going to talk eventually about something called a makefile, which lets you explain how this should happen, but then you don't have to actually ever type these things in. You just say make, hit enter, and it figures out what has to be recompiled. It makes life a whole lot easier. For now, I'd recommend just compile everything on the line. Just use a single GCC. I'm curious how far we can actually step into this thing. So you can see, like, at least the names of the functions that are being called, right? So do allocate buffer, validate vtable, IO do allocate buffer, fxstat. And you can get a fair amount of information about what's going on. Now, if you do this as a super user, you can actually get in and start debugging system level information, which is pretty fun, and sort of see the lowest level calls and how these things actually do I/O or disk access or things like that.
Seems to endlessly loop between certain values.
Which is probably a good thing, because I'm trying to output a string, And this CH, which I'm guessing is character, keeps changing. It was 117, it was 109. I'm guessing if you look up ASCII codes, you're going to find those are the individual characters of the thing I was trying to print. So there's 98 and 101. So those are definitely lowercase letters. 40 is punctuation. This is a great way to kill time, by the way. All right, and we're back at do right, which was enter a number, control D when done. I don't know. All right, and we're back. All right, other questions? So let's play with GDB a little bit more. And let's look at some pointers. Actually, let's do something more fun.
What's chat?
Car. All right, I got some code that does nothing. Gonna put on a -G switch. I'm gonna GDB pointer. And I'm going to say start, and it's going to put a temporary breakpoint at I equals 0, which is the only line of code in this program. But it tells me that it's inside a function called main, which was called with two arguments, argc, which was equal to 1, and argv, which was equal to this thing. And we know if we run a program without any arguments, argc should be 1. So let's do, okay, let's not do that. Let's put a break at main. So when you say, when you first come into GDB, you can say start to start your program. If you want to run your program with command line arguments, you can say run and then list the command line arguments, and it will start your program as if you had said program name followed by those arguments. So this is debugging my program as if I had said ptr space hello 42 bye, and I put a breakpoint at main to force it to stop right here in the very beginning. And now it's telling me that I'm inside a function called main. It was called with a value of argc equal to 4 and argv equal to this crazy number. So what's going on? So I can print argc and it's just equal to 4. I can print argv and it's equal to big weird looking hex numbers. When you see things with like 7 followed by a bunch of F's, you're looking at the stack. Okay, if you've done 270, same idea, it's a stack. It's usually where arguments to functions are placed. So this is not a number to be afraid of, right? It's a valid looking address. If you see zeros, those are invalid addresses. Usually something went wrong. So argv is equal to that number. So remember, we declared argv to be a car star star. So this thing should be a pointer to a car star. All right, so there's another command we can use in GDB, which is X. X lets us examine memory locations. So if I say X space and I put in this number, it will show me the contents of that memory location. And if I hit enter, it will show me the contents of the next memory location. So I'm going to make a memory map. How many F's do I have? Good. All right, so this is what argv is equal to. And at this location in memory, I find the following contents, followed by E7EB. And if I look at the next two locations in memory, I find the following. E7FE. And if I look at the next two locations in memory, which is 8H, let's see, I find the following. So we're taking apart the memory of the system here. And if I look at the next two locations, it's E807. And if I look at the next two locations, it's all zeros. So we're seeing here, maybe for the first time, what argv actually is. Argv is an array of these big long numbers, right? This is argv bracket 0, argv 1, 2, 3, and 4. All right, so there's argv bracket. E7F, that should have been an E, not an H. All right, so let's see what's actually in these memory locations. So let's examine this first location, E7EB. And it's got 6D, 6F, 6E, 2F.
6A, 2F.
Yeah. 6.9, 6E, 2F, 6.5, blah, blah, blah. So what are these things? These are ASCII characters. Okay, we know that because there's not a lot of F's and zeros popping up. So if I print argv bracket 0, P understands the nature of things and it will put them out in the right format. And it's telling me argv bracket 0 is /home/nic/224/ptr. That's the name of the program that I'm running right now, right? And 2F is a slash, 68 is an H, 6F is an O, 6D is an M, 6.5 is an E, and so on. So argv is this number here, which is the starting address for an array of 5 of these long numbers. The first entry in that array points to a location in memory that contains /home/nic/224, the name of my program. If I examine this next location, E7FE, this is an HELLO and a null terminator. that was the first argument, hello. Right, and I can print that. I'll just copy and paste. Right, I can print that. Right, and there's hello. And if I print argv2, that's 42. But if I actually look at that location in memory, right, it contains a 34 followed by a 32 followed by a 0. The ASCII code for a 4, ASCII code for a 2, and a null terminator. Right, so it's definitely a string. It's not a number. It's not an integer. It's just a set of characters. And everything in argv is basically a string. Whether it looks like an integer or a double or something else, it's a set of characters. Just like in bash, everything is just a string of characters. And when the system is trying to process argv, right, it will understand that this fifth element, argv bracket 4, is null, that represents the end of this array of information. So there's argv bracket 4, it's just a null terminator. But in fact, argv bracket 5 has stuff in it. And so does argv 6 and so on. And we saw this before in bash when we just printed out command line arguments. Okay, so that's just kind of a way to look at this whole argc argv thing. And it's a worthwhile exercise to actually sort of do this on your own and dig into these memory structures and try to make sense out of them. All right, so some junk code here, right? Function that takes an integer pointer and returns an int. I have a main program. I'm going to set y equal to 100. I'm going to pass the address of y to my function. My function is going to take the thing the argument points to and change it to a 5, and then return. And up here, let's just put in some prints. So we'll just print out the new value of y. All right, so we're in our main program. We're about to set y equal to 100. Now we're about to call our function. So we can print y is equal to 100. If I say print the address of y, it's equal to big, long, crazy number. Okay. If I were to look at that location in memory, I find this number 64 in hex. Right, that's 6 times 16 is 96 plus 4 is 100. That's 100 in decimal. So that's where my variable y is actually stored. This 7FFFE3A0 location in memory. And I can see the contents of it right here, right? When I call function, I'm not passing the number 100. If I say step and I get into function, function was called with one argument, which was big, long, crazy address, E3A0. That's the address of y. So my function now knows where this variable y up in main is stored, right? And when I say star num equals 5, it's going to say num is equal to this big long number the star says go to that location in memory, set it equal to 5. Okay, that's how this value is going to pass back to our main program. And now if I examine this address, it's equal to a 5. So there's no choice when I get back into main, when I look at the value of y again, I'm going to be looking at that same location. I'm going to see a 5. So I can say next and come out of my function. And now if I print the value of y, it's 5. So GDB is good for debugging, but it's also good for exploring. It's also good for trying to sort of relearn some of these concepts or nail them down a little better, because you can actually take apart the memory structures.
In the third to last command where you said next,
Mm-hmm.
after it showed the just 17 bracket, what instruction did it actually execute?
After it shows 17 bracket, nothing. So it should have done the return 1. I don't know why it showed me that. I think to show me that I was leaving the function, because the return should have brought me back, but yeah, I don't know why it showed the bracket first. That's a little weird, but it was on its way out. I think part of the trick might be the return instruction doesn't actually return, right? It asks it to pull something off the stack and load that into the PC and unwind the call frame and stuff like that. And GDB might be doing this in pieces. I mean, how do you write GDB? How do you do something like this? Usually there's hardware support for this. There's a way to say something like, after you finish each instruction, I want you to generate an exception, a software interrupt. And that software interrupt you write in handler, right, something at location 8 or 18 on the PIC, so that when that interrupt occurs, your code starts running, and it can say, okay, where did I come from? I came from, location 16. Okay, that was the instruction that was just executed. And you look that up in your little internal structures, and you print out the instruction, and so on and so forth. And it lets you step through one line at a time. So when I say go ahead to the next instruction, I basically do a return from my interrupt handler, which brings me back into my main code, executes one instruction, throws another exception at the end of that, brings me back to my code, and I can choose to print a prompt and wait for the user, or if they set continue, I can just let it keep continuing, and so on. So it's an expensive operation, right? When you're debugging, it'll run a lot slower, but since it's mostly interactive, we don't really notice that. And I've had code that worked perfectly in the debugger and did not work outside. And that was one of my week-long debugging trials when I was an undergrad. That's where I learned about instruction pipelining, because 270, right, we have this pipeline where we fetch and we execute and we fetch and we execute and we fetch the next instruction while we're executing the previous instruction, right? And I was trying to change the next instruction before it executed, but since it was already pre-fetched and was sitting in this pipeline, the pipeline on this machine was 8 instructions deep. Since I was pre-fetching this instruction, I would change it, but it wouldn't notice the change because it had already read it from memory. But when I ran it in the debugger, the next instruction was not the next instruction in my program, it was a bunch of debug code, and suddenly the program worked perfectly. So that was a week of my life I lost. But that's good. The longer it takes you to debug a program, the more valuable it is. Right? So when you've got a bug and you really can't find it and you're just like digging into it and tracing through it and you can't figure out what it is, keep at it, because you're going to find a huge nugget of gold at the end of that. Right? The bugs that are pretty easy to catch, after a while I used 1 equal sign instead of 2 equals. Those are valuable because you'll recognize them more quickly and you'll stop making those. The ones that really make you sweat and curse and cry are like hugely valuable. So my worst bug was 2 weeks. 5 hours a day I had to debug this thing. So it was like about 100 hours of debugging before I found the problem, and it was a heck of a lesson.
What was the bug?
It was a really subtle bug that had to do with writing macros, and I was assuming that the arguments of this macro were different from each other, and there was a fringe case where they weren't. But it was a senior project. It was a Z80 TRS-80 emulator, and I was booting a simulated operating system on top of the system. So it was virtualization, basically. And everything worked great, except if I tried to convert a number to hex, sometimes it would come out as G instead of 10. The F got bumped up to a G. And it wasn't my code, it was an operating system I had like found somewhere. So that was painful. All right, so let's talk about programming assignment 2, or number 3, since you already did 2. So PA3, you're back to bash, okay? This will be a bash script, and you're making another game, so this is a HighLow game. And let me show you how this works. So here's my file, HighLow. So it says, hello, welcome to HighLow. Please think of a number between 1 and 100, and I'll try to guess it. Hit any key when you have a number in mind. Okay, who wants to guess a number? Who wants to think of a number? Okay, don't tell us what it is, but you got a number in mind? Mm-hmm. Okay, so I'm going to hit a key. So the computer says, is your number 50? And you have to say, is your number higher, lower, or is that correct?
Higher.
Sorry. Is 50 high or low?
Low.
50 is low. Okay, so your number is bigger than 50. So your answer should be H if the guess is too high, L if the guess is too low. So 50 is too low. So we'll say L. Is your number 75?
Low.
That's low. Is your number 88?
Low.
94?
High.
High. 91?
High.
High. 89?
Yep.
Correct. All right, took 6 guesses to figure out what your number was. And high-low, you can specify whatever you want the top range to be. So we can go up to 1 million, let's say. So who wants to think of a number between 1 and 1 million? All right.
Yeah.
All right, you ready?
Yeah.
Okay, is it 500,000?
That's too high.
That's too high. 250,000?
That's too low.
Oh, my bad. That's too low. Okay. 375,000.
That's too high.
312.
That's too low.
343.
Too low.
359.
Too low.
367.
Too low.
I know what your number is. 371.
Too high.
Oh, I don't know your number.
Too low.
370.
Too low. Too low. Too low. Too high. Too high. Too high. Too high. Too low. Too low. Yeah.
Yes. All right. So 20 guesses to pick a number from 1 to 1 million. That's not bad, right? Because there's 1 million numbers you could have picked. So your goal is to make this game so that it does the most efficient job possible of figuring out what your number is. And it should also detect if you cheat. So suppose my number is really 50. So I'm going to change it to, 45. So I'll say that's too high, that's too low, that's too low, that's too low, that's too high, that's too low. I'm going to pretend my number was, 47. So we'll say 45 is too low. Well, now it knows that I was cheating. Right? And it knows that because I already said 46 was too high, 44 was low. It had to be 45. So you want to detect cheating. All right, so how do we do this as humans, first of all? How do we play this game? What's the algorithm?
Binary search.
Binary search. So basically, let's just go 1 to 100, right? you're told originally you're trying to guess a number somewhere between 1 and 100. It could be any of these 100 numbers, right? So you make a guess in the middle, and if that guess is too high, if 50 is too high, we know that 51, 52, all the way up to 100 will be too high also. And we've just reduced the problem to half the size. We only have to try to guess a number between 1 and 50. And we just keep doing this. Okay, is it 25? Well, 25 is too low. Can't be 24, can't be 23, can't be 1. And now we've cut our problem in half again. So after 2 guesses, now we only have to guess one of 25 possible numbers. And after 3 guesses, we have to guess one of 12 and a half numbers, right? And so the number of times you can cut this range in half is the number of guesses that you're going to need to make. Now when you cut this down to where it's got a range of 1, then you know what the number is, right? But you might stumble across it on the way anyway. The worst case is basically log 2 of n, and it's probably the ceiling of that. So integer log 2 of n plus 1 if it's not an int. So million, log of that is around 20. Right, a billion, the log base 2 of a billion is around 30. Trillion is 40. So number from 1 to a trillion you can guess in 40 tries, which is pretty cool. Okay, so let's look at the requirements and then let's talk about algorithms for doing this. So it's going to be a shell script. The name of the script should be HighLow. When you want to play, you type HighLow, you hit enter, print out a welcome message, right? Tell them they're playing HighLow, which keys to use during gameplay, H, L, and C. Ask them to think of a number between 1 and 100, and ask them to hit a key when they're ready. Don't start guessing as soon as they run this, because they got to have a chance to think of a number. So ask them to think of a number, hit a key when they're ready. User thinks of a number, hits any key, and then you start playing the game. So the computer makes a guess and says, tell me if that guess is high, low, or correct. The user types H, L, or C, and the program either makes a new guess or responds that it figured out what your number was. Continues until it figures out what the guess is, and then the game is over. Yes?
Do they have to hit any key and then enter?
No, so any key. So so if you say read-n1, it says wait for 1 keystroke. It doesn't have to be an enter key. So read-n1, and I put in a variable named data, waits for 1 keystroke, and then it prints out what the key was that was hit. If I say read-n2 data, I can type A and B, and then it comes back. And now data is equal to those 2 characters. So use read-n1 so that you don't have to hit enter.
Is there an equivalent to that in C?
Yeah, but it's a whole lot harder. You can put it into what's called raw mode instead of cooked mode, and it will basically return characters one at a time. But you have to play around with this function called IOCTL that basically conditions your input line, and if you don't undo it before your program exits, then your bash session is really weird. So, but it's fun to play with. All right, additionally, if the user runs HighLow with an argument, then you can pick a number anywhere from 1 to that argument. So HighLow 1000 is a game from 1 to 1000. And very, very important point here, if there is an argument given, you can assume it's a positive integer. You don't have to error check. Okay? So if there's any argument given, just assume it's a positive integer. And I will not test it with anything other than a positive integer. So if you say HighLow 1, you're guessing a number from 1 to 1, that's fine. But it's a good edge case to make sure your code doesn't blow up on.
Does it also mean it's fair to assume that you won't put a letter in?
I won't put a letter in, right? So in fact, my code will probably blow up horribly if I do that. Yeah. All right, so take advantage of that, right? It'll save you a lot of time. All right, details must be written as a bash script, must comment your code. So name, class, description of the program in the beginning, right, in your own words. Don't copy the assignment, but just something that says what it does. And comments throughout, right, telling me what's going on in different parts of your script. Don't require the user to hit enter. Just have them type HL or C. We'll go over the algorithm shortly. You've got to detect cheating. We'll go over that shortly also. Name the script HighLow. Next important difference, you're just going to upload this plain file to Canvas. Don't have to do a TGZ. Okay, don't have to do a tar. In fact, please don't. Just upload HighLow to Canvas, and I'll download it from there. All right, be sure of the following. The program is trying to guess your number, not the other way around. Okay, I occasionally have used this assignment before, and I get programs from students where the computer is thinking of a number and the user is trying to guess what the number is. And it's like totally backwards. Okay, so the user, the human, is thinking of a number, the computer's trying to guess the number. Okay. H means the guess was too high, L means the guess was too low. If you're thinking of 10 and the program says is it 50, the correct response is H, 50 is too high. Okay, don't get those backwards. Think of a number first and have the user hit enter after they've thought of it. If they say anything other than H, L, or C, just give them a polite error message. Right, so I'm thinking of a message that's low, I'm thinking of a number. If I hit an I, right, H if it's too high, L if it's low, C if it's correct. If I hit a 0, or I hit an enter, or I hit a space, anything that's wrong, just remind them what the options are and keep going. Don't give up on them. And as usual, feel free to have other people test your code. Right? Hand your program to someone, don't let them look at the code, but say, you know, try and break this. Because I'll try and break it. That's pretty much the whole assignment. I got on one page. That's pretty good for me. So questions about the goals here?
Does it have to be binary search, or can we mess around with other search methods? No.
I want it to be binary search, which we're going to go through shortly. I don't think you'll do better than binary search.
Well, I was thinking about maybe, because there's a human element to it, looking at expected probabilities.
Yeah.
Because yeah, when you take that 50, you're automatically splitting it into like 50-50, but people are weird and random. So
Right.
maybe if you set it to do 70-30 or something, sometimes it's wrong, but when it's right, you just cut it down to 30, not 50.
See, that would be a cool SLP too. You could like do a lot with that. Shoot me an email if you want to pursue that, because I'd definitely be interested in seeing that. So yeah, you could do a lot of things with this, right? You could play multiple games and try to figure out this person's habits, right? They only pick odd numbers, or they alternate between big numbers and small numbers, right? And you could start trying to sort of game them. And that would be pretty interesting. Yeah, that would be cool. Yeah.
Can I safely assume you don't want us to use random?
Correct. Yeah, don't just randomly guess. So we're going to go through the algorithm now for how to do this most efficiently. So here's the basic setup. We always need to know what the lowest and highest possible numbers are. So I'm just going to have a pair of variables. Low starts off at 1, high starts off at 100.
And this is our low, every one.
Say again?
And this one is our low, always one.
Low is always 1. High can vary depending on if they put an argument in, but the lowest number is always 1. The algorithm works regardless, but for simplicity, I'm just fixing that at 1.
Right.
Okay, so we're going to guess some number in the middle, which is high plus low over 2, the average. And since you're doing this in bash, if you say $paren high plus low close paren /2 close paren, it's always going to give you an integer value. Okay, it won't give you 50.5 in this case. It'll round down to 50. That's what you want. You don't want real numbers in here.
Is that high plus low or high multiplied by low?
Plus. Yeah.
Why do you use high plus low and not just high?
Because if the first guess is too low, so you guess 50 and that's too low, your next guess should be somewhere between 50 and 100. Right, so if I just take high divided by 2, it's going to guess 50. If I take the average of these, it's going to guess 150 over 2 is 75. So we're averaging, basically.
What if the number is not, like the ceiling is not specified and the user still chooses like 1 million and he keeps on pressing too low? Or is that just not something that would be tested for?
I'm having trouble visualizing what it would do, but let's find out. Oh, so yeah, if you just keep saying that it's too low, once it gets to 100, it's going to know that you were cheating, right? So if I say 100 is too low, it's going to say, oops. All right, so make a guess that's halfway in between, okay? So is it this number? If correct, then you're done. If you actually guessed it, you can do the happy dance and the game is over. If this number is too high, we know mid is too high, we know everything bigger than mid is too high. So everything from mid to high, we no longer have to guess. So what you want to do is set high equal to mid minus 1. And that minus 1 is really important. It keeps you from getting stuck. And if the guess was too low, then everything from low to mid is too small, so we can change our lower bounds to be mid plus 1. And then you just go back and you find a new midpoint between your new lower high and the high, and keep playing this. Now, what can happen if the person is cheating or forgets their number is high will end up being less than low. So if high ever ends up being smaller than low, you've detected a problem with their answers. And if you don't do this plus 1 minus 1, right, this may not happen. Or it may take you an extra try to find out. But high should always be bigger than or equal to low. Now it can be equal, right? For example, if low is 49 and high is 51, and you guess 50, and I say that's too low, then you're going to change low equal to 51. So now high is 51, low is 51, mid is 51. That's still totally valid, right? Because their number might legitimately have been 51. But if they say that 51 is too low, then you're going to change low to be 52, and now low is bigger than high. And you got a problem. Or if they say that 51 is too high, you're going to change high to be mid minus 1, high will become 50, and again low is bigger than high, and you've detected a problem. So we can go through this again on Tuesday, but that's your basic setup, right? Guess a number in the middle, adjust either high or low by that midpoint minus or plus 1. And at each time that you change high or low, see if high is smaller than low. If it is, then you can say something went wrong. If you do this, it will work, and it's a pretty straightforward program. All right, see you next time.